Continuing with our discussion from the previous video, we again start with an energy balance on a differential control volume. The control volume has a width of dx and encompasses the entire diameter of the circular tube. Thermal energy enters through the wall of the tube, resulting in a differential change in the mean temperature of the fluid passing through the volume. We then applied the first law to the control volume, and we then generated two expressions for the thermal energy entering the control volume. The first of these expressions came from an application of the first law, and the second comes from our definition of Newton's law of cooling. Equating these two expressions for the thermal energy entering the control volume, we were then able to obtain an expression for the differential change in the mean temperature as a function of x. In the previous video, we looked at the case when the thermal energy entering the control volume is from a constant heat flux applied to the wall. And we will now look at the case where the wall temperature is a constant. We will again have to consider two cases, one being the entrance region where the heat convection coefficient is a function of x, and the second is the fully thermally developed region where h is a constant. We begin this discussion by introducing a term denoted by delta T, which is this constant surface temperature minus the mean temperature at any x location. If we then take the derivative of this term with respect to x, we'll see that when we take the derivative of the constant value, it of course goes to 0, so we're left with a minus d dx of the mean temperature. We will then use this result and substitute it into our expression for the differential mean temperature obtained in the previous slide. And this results in a form that is now written in terms of delta T. We then separate variables and integrate the expression over the entire length of the tube, where Tmi is the mean temperature at the inlet and Tmo is the mean temperature at the outlet. We then evaluate these integrals, and at this step we multiply and divide by the full length of the tube. We can then simplify this expression by combining the logarithmic terms on the left-hand side and by noting that the bracketed term on the right-hand side is by definition the average heat transfer coefficient for the length of the tube. And we note that the average convection coefficient encompasses both the entry and thermally fully developed sections. Recognizing that we are still looking for an expression for the mean temperature as a function of x, we can then apply the exponential to both sides of the equation. And we can then adjust the limits of integration from 0 up to an arbitrary point x. And then this will give us the expression that we're looking for. But in this case, the left-hand side is still written in terms of a non-dimensional temperature. We will return to this expression in a few minutes, but first we would like to take a look at the previous expression, rewriting it in terms of the average heat transfer coefficient, and we will use this result to formulate an expression for the total amount of thermal energy required to raise the temperature of the fluid from its initial temperature to its desired outlet temperature. To do this, we'll again return to our definition of delta T, and we will now write it in terms of the outlet temperature. And this gives us a way of expressing the mean temperature as well as the inlet temperature. Now, if we make those two substitutions and then simplify the expression, we obtain an expression of the required amount of thermal energy in terms of delta T. Now, returning to the previous expression, we can rewrite it in terms of m dot c sub p, and we can then substitute that into our expression for the total thermal energy, which then results in the desired expression. We will then define the term in the brackets as the mean log temperature and the expression P times L as the total surface area. And this gives us the standard formulation where the total amount of thermal energy that's convected through the tube by the mass flow rate is equal to the average heat transfer coefficient times the surface area times the mean log temperature. And the log mean temperature difference is the appropriate average temperature over a tube of length L for a constant surface temperature condition. Returning to this expression that gave us the mean temperature profile in terms of a non-dimensional temperature, we can then multiply through and obtain an expression where we just have the mean temperature on the left-hand side. This can be plotted, and we will see that the mean temperature as we move through the tube will asymptotically approach the constant wall temperature. And we clearly see that the expression for delta T changes as a function of the position along the tube. This is in marked contrast to the same situation for a tube with a constant heat flux passing through the wall. It is for this reason that when we need to determine the average temperature of the fluid within a tube with a constant temperature wall, that we have to rely on the use of the log mean temperature difference.